So we have homology and cohomology. Okay. So what are these things? These are basically, let's say, techniques to sort of try to detect holes, let's say, okay, and different kinds of holes. So they sound like similar words, but they're actually very different, at least in the way they're formulated, okay? So homology is sort of like a geometric approach, let's say, geometry sort of approach to define a hole. And cohomology is like a calculus sort of way, okay? And now I'll explain the sort of relevant stuff to, since we have first years here, I guess. I'll explain some relevant theorems, because basically what we're going to be doing in both cases is generalize theorems that we know and use them to find holes, right? So basically, what do I mean by find holes? Like, it might seem like a silly, like a circle, okay? A circle has a hole, okay? Like if we think of it as a topological space, like X. X is the circle. But not really, in the sense that if you are in the space, if you think locally, right? Like, where's the hole? You know, like if you live on the circle and you just walk around on the circle, you don't notice the hole. So that's sort of the challenge. Like, how, if you live within the space, right? How can you detect that there is a hole there, as opposed to a flat line? If you live on a flat line, if you look only within the space, how can you detect that, okay? That's the idea that both try to do in very different ways. But then we'll see that they're linked, and that's why they have similar sounding names, okay? So basically, let's look at, so how does it work, okay? Both try to exploit the fact that usual rules which work in Rn, in Euclidean space, fail in spaces which are weird, basically spaces which have holes. Basically, if spaces have holes, the usual rules don't apply anymore, okay? So let me give you an example, okay? If you have the plane, right, R2, if you draw a curve, so if this is the plane, the XY plane, there's a well-known theorem called the Jordan curve theorem, okay? If you draw any curve, any closed curve means it ends, you know, starts and ends in the same place, then it splits space into two, right? The inside and the outside. It bounds a region, and it has an interior and an exterior. Now, this is not, so this is the Jordan curve theorem, right? If you draw a closed curve in R2, you split the space R2, right, into two disjoint sets, right? So if you include the boundary in one of them, but usually you exclude the boundary altogether, and they're disjoint or non-overlapping sets, okay? This is false if the space is not R2. Okay, so let me give you an example. If you have, say, a torus, okay? I mean, this is, I don't know. Okay, let's say if you have a torus, okay? If I draw a torus like this, let's say, right, so a torus. If you draw like a curve, a loop, just around the hole like that, within the torus, it's not bounding anything. So it's an empty interior, you see? I mean, that doesn't have to be this complicated. Even if I just got a square and I punch a hole in the square, that's the space, and the curve is that sort of, you know, let's say that the boundary is included in the space. If I look at that curve within the space, there's no interior, right? So this is like a way of detecting holes. That's the idea behind homology, okay? So let me be a bit more precise. I'm not going to be too technical because, I mean, you know, you can look at what's it called, Lee, the book, you know, Introduction to Smooth Manifolds. But basically the idea is, so what is a curve, first of all? A curve, I think Prof mentioned this in his lectures, it's a continuous function from the unit interval, right? So you get 0, 1, and you map it to the space, okay? So you can think of like the interval and you're sort of doing something like that with it, like stretching it out and so on, right? Now, if you have a 2D space, let's say, okay, then you can have like a generalization of the curve, right? So this is like an image of the unit interval, continuous image. If instead you take the unit square, right, the 0, 1 squared to the space, that's like a sort of square which you sort of deformed a bit like that, right? And so on. And if you take a 3D version, you can think of it as like a, right? So it would be like a sort of curvy cube, I guess, I don't know, right? But it could, you know, it could be a sphere, it could be anything, really. But a continuous map of the unit cube, okay? So these are called chains, basically, okay, in algebraic topology at least. This is called a 1 chain, 2 chain, a 3 chain, right? In general, if you have k copies of the unit interval, mapping to the space. This is called, and it's continuous, right? It's a K-chain. Okay. So, any questions about this? Okay. So now, then we define an operation on chains, okay, called the boundary. Okay. So if you have a chain C, okay, the boundary of C is, well, it's another thing. It ends up being another chain called del C, right? A sort of partial derivative symbol, basically. So the boundary of a one chain would just be the two endpoints, right? That would be the boundary. The boundary of this, so this is the image of the unit square, okay? So the whole thing is the chain, including the interior. The boundary of it is this, right? That's the boundary. You know, it's quite intuitive. In this case, the boundary of this is like the, so the chain itself is the entire cube. The boundary is just the faces, okay? So you might notice this is basically taking the boundary of this gave us like a curve, okay? And taking the boundary of this gave us sort of like a, not exactly something like this, but like something which could be an image of a square, right? So it's like a 2D object, the boundary. So like the dimension is going down, okay? So the boundary of a 3 chain is a 2 chain, the boundary of a 2 chain is a 1 chain, and so on, okay? So basically, yeah, so this is, so now I'm trying to generalize that theorem I mentioned earlier, the Jordan-Kf theorem, and sort of trying to approach this idea that it fails, okay, and use it to define a whole. I'm trying to get a definition of a whole, basically, okay, using these objects called chains. So basically what you do is, you can get like the, so if you have a topological space, okay, you can define, with appropriate conditions, I suppose, right? You can define the set of 1 chains, okay, all the 1 chains, and then all the 2 chains, and so on, and all the K chains, and they form a chain, if you like, right? And each of them is a vector space, okay? So I'm not going to get into like the operations and so on, like how they're defined, but basically they're vector spaces, and the del, right, the boundary is, so let's say this is like 2 chains, right? And so on, there's a chain of these. But the arrow actually will be pointing this way. So what do I mean by this arrow? Like, this is a linear map, okay, from here to here. So if you get 2 chains, this is a linear map from 2 chains, sending 2 chains to 1 chain, and so on, right? So this is also, and so, and it's, you can keep going up like that, okay? So basically, what you do is you get the set of all chains, okay, which have a 0 boundary. So let me use the letter phi for this, okay? So all chains which have a 0 boundary. Now what this means to be a 0 boundary, so this is not literally equal to 0, right? It's like the set 0, but I'll explain what I mean by this in a second, right? But we usually just write this, okay? And we quotient out those chains which are boundaries of some other chain, okay? So I'll explain this. Let me just write down the definition though, such that there exists, let's say, psi, such that phi is the boundary of psi, okay? So first of all, even let me explain a bit about quotienting, because this is sort of even the way topologically we join things and so on, okay? So those of you who have done like groups and so on, you probably recognize this idea of like have a set, an algebraic structure of some kind, a group, a vector space, a ring, whatever, and you divide it by another set, okay? Now the best way to think about this, in my opinion, is to think about this denominator set as the set of zeros, if you like, okay? Now, when I did that talk on, what was it, quadratic reciprocity, I defined the modular arithmetic as Z, but we decide like that, let's say 12 is 0, right? If we decide that 12 is 0, this has other consequences, like 13 is 1, and 24 is 0 as well, and so on, right? So basically, it turns out that if you decide that 12 is 0, and you keep all the axioms, the ring axioms of Z, the usual rules of arithmetic, basically, you get that every multiple of 12 is 0, okay? So the way an algebraist would write the integers mod 12 is by doing Z all over 12Z, okay? So 12Z is, literally, this is the set 0 plus or minus 1, etc. The integers divided by 0 plus or minus 12 plus or minus 24, okay, and so on. So this set represents this set, if you like, with these all made equal to 0, to each other, basically, okay? Another example, which is more topological, I suppose, let's say you get R and decide all the integers are 0. Okay, what is this? Don't have any idea what this is? What would that look like? If you get the real line, we don't need to think in 2D, but yeah, you get the real line, say 0, 1, 2, right? So if you get a point here, like 1.5, like we said, the integers are 0, right? So you can just subtract 1. It's the same as 0, so it's the same as this point. Even the point here is the same as this point. Basically, it's sort of like Pac-Man, no? Like when the little guy sort of goes out here, he comes back in here again, right? So basically what you've done is sort of connected 0 and 1 together, right? 0 and 1, and it's become a circle now, okay? So it's like you got the unit interval and connected 0 and 1 together, right? You made 0 equal to 1, because in this set, there is 0, 1, 2, etc., and they're all equal to each other. So we got the real line and made the integers equal. So this is topologically how you would join, right? How you'd make a circle out of the, in fact, this is like, people just call this a circle usually, okay? If you don't know, if you see this notation, it's the circle. Another way you could do it, for instance, is, let's say you can get R2, right? And divided by Z squared as well. So all pairs of integers, this would be like a 2D version of this, like a square, okay? Where you go out here and you come back in here, and you go out there, you come back here. This is basically a torus, okay? It's a torus because if you connect it like that, but also in a 2D way like that, you get a torus, okay? So yes, so I'm using this operation of quotienting here. Back to the homology now, okay? So basically what we're doing is, we're getting all the chains which have a 0 boundary, and a hole is basically something which doesn't have a boundary, okay? So such that if there exists another thing which it is a boundary of, we equate it to each other, okay? So all those which are boundaries of other things are equated to each other. So the number of chains we're left with, if you like, well, not exactly the number, but what you end up with is getting only the chains which bound a hole, okay, in here, almost, okay? Because what you get here is actually, it's a vector space, okay? It's called the Kf cohomology group, okay, of the topological space. And it's a vector space, this thing, and its dimension is, no, it's not I'm not sure if it's a vector space or not. It is a vector space, yes. It's a vector space, and its dimension is the number of holes, okay? So the number of holes, basically, is the dimension of this, okay? So dim of hk of x, okay? Don't worry too much about the technical stuff though, but basically the idea is this thing I just mentioned, okay? Where you have this generalization of the Jordan curve theorem, right? Where if you bound something and there's nothing there, that's how you detect holes in homology, okay? So have any questions about this? Uh-huh. Yes, yes. So it's like there's different ways to bound the same region, sort of, right? Or bound the same hole, let's say. And we're saying we're bounding the same hole, right? So basically, if there's a hole, right? Like that thing on the torus, right? You can bound it like this, you can bound it like this, you can bound it like this. We're bounding the same hole. But you can reach this just because it's like the boundary of something else, right? So this can be deformed to that, sort of, and so on. That's basically the idea. You're equating them all, okay? That's very loosely what's going on. But that's the idea, okay? So we're counting all of these as one chain, if you like. Okay, so now let's look at cohomology, which is a different way of trying to formalize the idea of a hole, okay? Also, notice I didn't really get into this idea, but there are different kinds of holes as well, right? So if you have a circle, it has a hole, right? It's like a one-dimensional hole. I didn't really mention this that much, but there are different kinds of holes as well, right? If you have a sphere, right, a hollow sphere, it does have a hole as well, but it's a different kind of hole, right? It's like if you imagine a hole is basically the absence of a space, sort of. That's the way to define it. So in the sense that this hole, if it weren't there, it would be like a, the space itself would be two-dimensional, if you like, right? Here, the space would be three-dimensional, right? That makes sense, like if you're to fill it out, but we're getting rid of that, right? But the dimension of the hole is one less, so this is called a 1D hole, and this is a 2D hole. Right? But anyway, this homology, apart from detecting holes, because I said it's already difficult to detect holes locally, it distinguishes these different kinds of holes, the dimensions of holes as well. Okay. Okay, so should I rub off? Can I use this board? Okay, tight. Now, so let's talk about cohomology now. So this is different. Now, before we get to it, though, I just want to at least emphasize for the first years and so on, at least the facts of calculus. Okay, so remember, what did I say? The standard sort of known theorems for Rn fail when you have holes. Okay. Now we're going to the same idea, but for calculus. So basically, the standard facts about calculus fail. Okay. So for instance, a very primitive one, let's say, is that if you differentiate a function, or sorry, if a function has zero derivative, then what is that function? A constant, is that so on? Now this fails on spaces which have a hole, right? If you get, for instance, the real numbers, and you remove 0, right? And you define f of x as being equal to 1 on x, say. Okay, it doesn't even have to be that, it could be just two different values. Oh no, actually, well, this won't work. Sorry, obviously the derivative isn't constant. Let's do a function which is -1 and 1, right? -1 for positive and 1 for negative or something like that. Oh, this is weird. Let me do it this way, like that. Okay. So the function looks like this and then this. Okay. This is differentiable everywhere, right? And continuous everywhere as well on its domain, because the domain does not include the origin. Okay. So since the domain does not include the origin, basically because there's a hole, right? So the derivative is constant. It's well, the derivative is 0, but it is not constant. Let me phrase it that way, right? So it breaks this. Why does it break it? Because there's a hole. Okay. Obviously, I'm not saying this is a false theorem. This is the theorem. I'm not writing down the conditions. It has to be on R and so on, or on a space. If you want to generalize it, something without a hole, right? Because if there's a hole, it fails. Okay, so this is, you can use this as like a test. So what is f prime? I mean, f prime of x is 0. The derivative is 0, but it is not constant. So at the hole, there is nothing because it's not part of the domain. So that's the idea. This function has analogues, okay, in like 2D. So not this function, this theorem, if you like, has analogues in 2D, right? I always forget these because I don't know, they feel a bit physicsy, right? So I guess it's this one, right? If curl of a vector field is 0, then what can you say? You can say it has to be the gradient of another field, right? So basically, f has to be grad of something else. The gradient of some g or something, right? Oh no, that has to be a function in Butler. Whatever, right? So basically, that would mean like, so if you imagine, so the curl, what does it mean if curl is 0, right? Curl of a vector field is 0. It means the arrows aren't really turning, sort of, right? So that would mean that the function comes to rise as being a gradient of a function of two variables, right? But if you imagine like this sheet of paper, so if it's the plane, say there's arrows pointing everywhere, that's like f, right? And if they're all in this paper, then the curl is 0, and this will be the gradient of some function. But if you can do this sort of thing, right? I join them to a quotient on this like line, if you like, right? Then all of a sudden, the curl isn't 0 anymore, right? Or no, sorry, the curl is 0. The curl is still 0, right? But f is not necessarily the gradient of some function, right? And basically, it's because there's a hole here, right? So that's basically it, right? And then there's the 3D version. I guess it would involve the divergence, I think, right? Here I wrote it like this. So it's the curl of something, right? There exists G. Here there exists F, right? But these are basically 2D and 3D analogs of this, right? I haven't done vector analysis in quite a while, so I'm a bit rusty on these. But okay, so these are fundamental facts. So the point is, especially for those of you who are unfamiliar with this, just think about the fact that this has 2D and 3D analogs. Basically, that's the important thing, right? And and dimensional analogs. But actually, it's quite difficult for those of you who are familiar with these. Like, how do you generalize this? And as in, well, not how we generalize. We just did generalize them. At least they're here, the generalized version. But how do you generalize them beyond this, right? How do you sort of get one, like curl here? This is a vector field. Here it's a function. Here they're both vector fields. Here they're both functions. It's quite difficult to get like stated for all n, if you like, right? So before I address that question, I want to mention something else, which we'll get to shortly, right? Which is basically the fundamental theorem of calculus. Just because if there's like 6 formulas here, I guess you would be familiar with it, but maybe you would not have explicitly called it that, right? So the fundamental theorem of calculus also has analogs, and we're going to discuss those as well after we discuss these. So what is the fundamental theorem of calculus? Basically, the idea of both the fundamental theorem, I guess this is the second fundamental theorem of calculus, right? For those of you who split it into 2 theorems. But basically the idea is that if you want to see the change of a function between a and b, okay, so how much the function changes, like f of b minus f of a, it's basically the same as adding up all the tiny changes, right? Like you do this change plus this change plus this change. That's a very informal way of doing it, but basically, what is the change, right? How much is a change? Well, a tiny change is the base, right? So it would be so the rate of change times how much the change is, right? So the rate of change is the derivative, right? The tiny change is dx. And if you sum all these up from a to b, right, it's basically the overall change, f of b minus f of a. So the overall change, this bit, f of b minus f of a, is the sum of the tiny changes, okay? We probably never, or if I don't know what your teachers did in your different schools, but basically you might not have seen it explained this way. And this is the way you need to think about it if you're going to understand the generalized version of it, right? So basically, yeah, this is the fundamental theorem of calculus. Basically, the fact that differentiation and integration are opposites, sort of. Right, so that's the FTC. Now, then what are the generalized versions of it, right? There's like, there's Gauss theorem, which I think is the 3D one. Then there's Green's theorem, I think is the PDX plus QDY, right? I can't remember how to write out the formal statements, but basically, even if I remember the proofs a bit, right? So, for instance, Green's theorem, if I recall correctly, you have a region, and you're integrating along it, right? A curve, sorry, you're integrating along the curve, and basically the idea is to split it up into like 4 tiny ones, right? But these, and they go around this way, right? And these end up canceling each other out, right? That's the proof. Which is a very loose proof that I remember doing in vector analysis. But that's the idea, right? That the tiny changes add up to give you the whole thing, right? So even though it seems more complicated to do the tiny things and add them up, you get nice cancellation, and it ends up being the whole thing, right? And this will have a general, the same way that we try to generalize these, we try to generalize this as well. Okay, both of these things we will generalize in general. But the way we do them is with the thing Jake mentioned earlier, differential forms, right? What are differential forms? Well, basically, they're a formal object, if you like, which exists to sort of solve this problem. At least, I don't know if there isn't a visual way to understand them. At least I haven't been able to, whenever I've looked at them in a textbook, they never explain it other than giving it formally. So I don't know if there exists one. But basically, a differential form is something which exists to be integrated, right? So something like this, okay, f of x dx, that is a differential form, okay? Its purpose in life is to be integrated, basically, right? You integrate it along a curve, I guess. Right now, here I'm starting to, I want to start to link a bit with the homology ideas, right? So, or at least with the terminology I introduced there. So basically, yeah. So this is called a differential one form. This thing, not without the integral, this is called a differential one form. Okay. Now, what do you do with differential one forms? You integrate them along a curve, right? Or a one chain, if I use the terminology from before. So they get integrated along a one chain, right? A differential two form is something like this, right? That's the like vector product, if you like. So it gets double integrated, right? Along like a two chain, right? So which is like a region, but we think of it as like an image of the, right? So it gets integrated along one of these and so on. Well, the boundary of a region, and orientation is important, right? As it is with curves. And then there's a 3D version, right? F of x, y, z, dx, dy, dz, and so on, right? So these are what differential forms are. Now, the point about differential forms is you can also relate them to each other. Well, yes, you can. So you can differentiate. You can apply this thing, the d, okay? And this is basically the exterior derivative, it's called. So what is its goal? Its goal is to generalize these ideas. So curl, gradient, divergence, and so on. The generalized version of it is basically this d operation, okay? But the distinction is that d, you give it a k, let's say a k form, right? So one of these, let's say a one form. If I were to apply d to this, I would get a two form. Okay, so you give it a k plus a k form, it gives you a k plus one form. So the dimension increases. Okay, this is in contrast to this thing that I mentioned earlier, the boundary operation. Okay, the boundary, you give it a k form, and it will give you a k minus one form. Okay, so there are some similarities, but this is definitely a distinction between the two. Okay, now. So, but these are the broad ideas, okay? So now what you do is can you define a whole, okay? To define a whole, we appeal to this sort of reasoning from before, okay? Sort of looking where this idea is, where where you have something which is analogous to this in many dimensions. So what would that be? Basically, the condition that needs to be is, you need to look at something, a form. Okay, it looks, okay, let me write it down and you'll see what it looks like. So there's loads of ways, again, to bound the whole. So I need to sort of quotient out the equivalent ways. And basically, it ends up being this, okay? So you need to look at all the forms, okay? Which have zero derivative, but zero exterior derivative, okay? But they are not the forms of some other derivative, okay? So if there is another thing, we just treat it as equal to it, right? So let me say omega prime such that the omega prime equals omega, okay? And here you end up with a group, okay? Also these things, right? So it's a linear map, D. Linear map from K forms to K plus one forms. They form this chain structure, very much similar to that, okay? And this is called the Kf cohomology group, okay? So, and it's a vector space, and basically its dimension is another way we try to count holes. Okay, now it is a very sort of abstract. If you've never seen this, it's like there's loads of layers of definitions to it. Here, this is what we use to define, or at least for this talk, we've defined the number of holes, which is, an informal notion. We've defined it as a dimension of this. But here I've given like a different possible formulation for the number of holes, okay, in a space on a manifold. So the question is, are they the same? Right, so it's difficult to, it's a very different definition, right? I mean, again, if these are quite abstract, but if you just think about the two different ways we've gone about defining holes, okay, with this example and the example of looking at the boundary, right, bounding nothing, sort of. But basically, yes, it turns out that they are the same, okay? In fact, these two groups you end up with, the homology group and the co-homology group, are isomorphic. And this is the celebrated de Rhams theorem, okay? So de Rhams theorem is basically de Rhams theorem states that basically this the kth cohomology group is isomorphic to the kth homology group. Okay, so they're the same. They measure the same number of holes, and it's a very mind-blowing fact, I suppose. I mean, it's very difficult to understand the if you go through the formal ideas, but to really get it, it's I'm not sure I fully understand it myself yet. I mean, I don't know. Like, I obviously intuitively this measures holes, and this also measures holes, and the reasoning is very similar. But to understand why it's similar, and the proof. So, what is the isomorphism that is used? Basically, it's an integral, I believe. If you're going from if we're going from chains to forms, right? To map a chain, right, or a representative, I suppose, because we've quotiented out, right? The map is it's unique. It turns out to be unique, right? Such that if you integrate over the chain, if you integrate the form over the chain, it's 0, and that's the isomorphism that you need, right? And there is a unique form which makes it work. Unique is an up to quotient thing, right? And that's basically the proof of the Ram's theorem. But also, apart from this, okay, something which is also maybe more something which is would appeal to what we were familiar with already, right? The fundamental theorem of calculus and its generalized versions. And I say this mainly to the undergrad students who've sort of done vector analysis, right? Basically, Stokes' theorem is a generalization of the fundamental theorem of calculus. And what is Stokes' theorem? Using this language, Stokes' theorem basically tells you Stokes' theorem is that if you want to integrate the derivative of some form over a chain, right? It's the same as integrating the form over the boundary of that chain, okay? So basically, what does this mean? Here, the dimension, remember that I said the dimension goes up and down and so on. Here, it's basically being retained, right? Here, let's imagine like you're integrating over some 3D thing, but you're taking the differential of what you're integrating first. Whereas here, you're integrating the form itself, but over the boundary instead, okay? That's basically the most, it's like the most concise way to state the fundamental theorems of calculus to arbitrary dimensions, right? And I think this is the nicest, this is the most appealing, this is the thing that made me want to give this talk particularly, is to try to shed some light, because I've always seen this, in differential geometry texts and so on. Like this is the most, to me, this is like a very nice way, like, Green's theorem or whatever, like with the px and the y, like it takes like 10 lines to state it for me, whereas this is like a very nice one-liner. It's very profound. And I think I said everything I wanted to say, unless you have any questions. Shazmo? That's it. Thank you. I mean, I don't know if this was a good balance of like not going into the gory details of this. But if you, yeah, ايوه issa W prime mhux qed nuża bħala derivative, just like another nagħmel like ma nafx x'inhi oħra. I don't know. V nafx right? Le mhux prime, sorry, ma kontx naf se nagħmel called prime. Għax dejjem omega ma nafx, jew no forms. Ejja, le, sorry. Għax ma kontx naf se nagħmel omega prime rid nagħmel. Tajjeb, meħle, diki. Tajjeb, u kif qed tara mbagħad once tarom hekk tinduna and then there's like algebraic versions of generalizing this even more to like just general chain structures they're called insomma. And then it gets like to ridiculously abstract sort of, I don't know. What other cases there could be. These are a bit strange, just per esempio, like if you want to do concrete examples, because I didn't really get into the concrete examples. For instance, the homology group of, say, the circle, right? It's Z, or like the homology group of so this H1 of the circle is Z, okay? But basically, so I don't really know, personally, I don't understand the intuition of why it would be Z, but it's one dimensional in the sense that it has one generator, right? It's like a group generated by one element. So in that sense, like a free abelian. So you can go one loop, or you can go two, or you can go one minus one. Oh, okay, okay. It doesn't matter how you would go, because it's going to be homomorphic to that. So what does it mean? So if you do like two loops, it will be the same as one, as in you end up. Yeah, but Z is because like for each element in Z, you can have a class of. Oh, okay, okay. That's what it is. Okay. Because when I Googled it, I think that, or I looked at it on like Math Stack Exchange, and the answer was it's difficult to find like one unified understanding as to why the homology group ends up being what it is. Because these are the easy examples, like Z, that's Z, or if it's a torus, I think it's Z for one, I think, and Z cross Z because for one, yeah, for one dimensional hose, I think it's Z cross Z, no, because you can go like this on the torus. Two dimensional hose is just Z because there's only one 2D hole, which is like the interior of the torus and so on, right? And the rest of them are zero, right? Yeah, so that's another example. So just so that you get what I'm saying, if you have a torus, right, like how many 1D holes does it have? Remember I was explaining this idea, like the interior of the donut, there's only one of those, right? So the second cohomology group is Z, which is one dimensional. The first cohomology group is Z cross Z, which is like a direct product of, you know, the group itself, or the direct sum, whatever, doesn't matter, right? It's two dimensional. Why? Because you can, there's like a hole like this, right? But there's also a hole like that, sort of, right? You can loop like that or like that, sort of, right? Yeah, so I guess that's the end of my talk, right?